In this video, we are looking at min-max problems for circular motion. Specifically, that looks like the tops and bottoms of circles, that kind of thing. We want to be able to solve this kind of problem because they are not actually uniform circular motion. They're cases where the velocity is changing, not just in direction, but also in magnitude. We'll talk a little bit more about why that can be later, but for now, we want to look at some extreme situations, right? We've already talked about this in our question, but this was a really fun photo of an old school version of one of these barrel rides, right? What's holding you against the wall? Well, really, it's the normal force of the wall pushing you inward, right? That's what's actually going on. The force of static friction keeps you from going downward. That's what's going on, right? Centripetal force is center seeking. We have the static friction up, the force of gravity down, and the normal force in. Centrifugal force with an F is something you often hear about, is basically means center fleeing, flung out of the circle. But there is no force pushing you outward when you're in one of these rides, right? It is the normal force keeping you going in a circle. Without it, you would go in a straight line. That's just inertia. That's not a separate force, right? It feels like it. And so there's some interesting things there that we can talk about. Why does it feel like that's happening? And again, this is really just inertia. So if you imagine a car making a turn, right? You're in the back seat with no seatbelt, right? You're in that little spot in the back corner. And as it turns, right, what you experience is that you're pushed across the seat and you end up on the other side sliding across, right? That's what you experience. But you're just obeying Newton's first law. You're just obeying the law of inertia. You're just traveling in a straight line, or at least trying to, while the car moves around you, right? Until now you're being pushed by the edge of the car. There is now a centripetal force pulling you into the circle. This happens all the time. If you make a fast, sharp turn in a car or any other vehicle, you can feel the objects move relative to the car, and they do move relative to the car. That's totally valid, but they're not being pushed by any actual force. They're just moving in a straight line according to inertia, which is Newton's first law. So the centripetal force in this case would be the normal force from the side of the car, right? We call the centrifugal force fictitious or fake. It's just due to inertia. Sometimes this is called an inertial force, and it really only is something that you can kind of experience if you're in a non-inertial reference frame or an accelerating reference frame. We don't put it on free body diagrams. It does not exist. There is nothing pushing in that direction. Right. So when we talk about minimum and maximum cases here, which is really our goal in this video, the water in the bucket problem we talked about is a good example. A loop-to-loop going in a roller coaster, catching air off of a ramp, a string breaking as something is spinning, or making the curve without sliding out of it are all examples of this. So the back to the bucket of water scenario, right? We've talked about this. What do we need to keep it from falling out? How do we find the minimum possible velocity that you can go around to keep it from falling out? We know, right, that in this problem, it was the force of gravity plus the tension, well, the normal force that kept the water in. And we know that when you went slowly, it would fall out, right? So we need to figure that out. Then there's, if you imagine riding a motorcycle around a trick loop, right? If you go too slow, we know you're going to fall down. And so let's practice this problem, right? Starting with a free body diagram. If you're at the top of the loop, we have a force of gravity and a normal force, both pointing toward the center, both down, right? The force of gravity is, of course, there no matter what we do, always pointing down. And the normal force points down because you're at the top of the loop and the ground is now above you. Right? So the normal force plus the force of gravity makes up the centripetal force, which equals mv squared over r, mass times the centripetal acceleration. So as we go slower and slower and slower, as that v gets smaller and smaller, the net force then gets smaller and smaller, or the centripetal force. But the force of gravity cannot change, which means the normal force keeps getting smaller and smaller as you go slower and slower. And at some minimum velocity, the slowest you can go, because we can't eliminate Fg, we have eliminated the normal force, and the normal force goes to zero, and our solution to what is our minimum velocity comes from the force of gravity is the only component or the only piece of the centripetal force. So that means V min is the square root of R times G, which is a pretty simple result, actually, which is kind of nice. We can, for a particular value, we were told this is a 1.5 meter circle, radius circle, and that tells us that we have to go around at about 3.8 meters per second. What about the opposite? What about catching air? If you're going on the outside of a circle, right, over a circular hill, the faster you go, right, the more likely you are to fly off as a projectile. And so what is the fastest you can go before you do that, where you're still just barely in contact with the road? In this case, the circle is a radius of 25 meters. Well, if we draw the free body diagram, in this case, the normal force is now opposing the force of gravity, right? If you go really, really slowly, right, it's mostly normal force with a little bit of, we've got big normal force that's almost as big as the force of gravity, so just a little bit of net force down. But the faster and faster you go, that normal force has to get smaller and smaller because it's out of the circle and it's the thing that is reducing your centripetal force. So as the normal force goes to zero, just at that instant, we have reached the point where we're just starting to lift off from the surface. No touching the surface, no normal force. It's interesting because then we get the same result, that the force of gravity mg is equal to the centripetal force. And our result ends up being V max, in this case, is the square root of Rg, which for this particular example is about 16 meters per second. So let's think of this a little bit more theoretically. If we think of spinning a circle, an object around a circle vertically, maybe a yo-yo at the end of a string, and it has some maximum tension that the string can handle before it breaks, right? Any object has this breaking point. Where is the string most likely to break if we're spinning it around this circle? Well, the answer is at the bottom, because if you think about the free body diagram at the bottom, the force of gravity is down and the force of tension is up. And if the force of gravity is down, it is out of the circle, so the force of tension must completely counteract gravitational force, plus give enough force to pull it into a circle. And this is the point where the force of tension will be biggest, and therefore is the most likely place for it to break. We could also ask ourselves, well, at what speed will this break? And for that, we need to know what this F tension max will be. If I tell you that we have F tension max minus the force of gravity, that's the centripetal force, equals mv squared over r, then we could solve for v, and we get that it's Ft max minus Fg, the centripetal force, times r divided by m, and then take the square root. Depending on how big that force of tension max is, we would get a bigger velocity. So the stronger the string, the faster we can spin the circle. Another one of these is how can you drive safely on a curved road, even if there is, say, no static friction, right? Completely iced. Well, if we use a banked curve, something like this, then we can use the normal force to keep us in the circle, and we don't have to rely on friction at all. You don't have anyone to talk to here, but why does this help? Well, normally on a flat surface, the normal force and the force of gravity are perpendicular to the circular path you're trying to drive. But if you go on a banked curve, then the normal force, part of it is pointing into the circle. So if we draw our free body diagram, normal force perpendicular to the bank, force of gravity straight down, the radial direction is to the right or into the circle. Now the radial component contributes to the centripetal force. Right? Which is bigger, the force of gravity or the normal force? Well, the perpendicular axis has to sum to zero, right? It has to have the force of gravity and that component and normal force be the same. So those two are equal. And the normal force must be bigger because it can't be equal to just one of its components if it has both. So the ramp angle here, notice again, the angle is, the angle of the ramp is the top angle there. So we could do an actual problem here. If we want this ramp to be able to allow an object or a car to go around it at 20 meters per second, even in the iciest of conditions with no friction, and the radius of the circle is 200 meters, how much angle do we need? Well, the radial component, the radial force, net force is the centripetal. that is equal to Fn sine theta, which is equal to mv squared over r. In the perpendicular direction, Fn cosine theta, the perpendicular component of the normal force, is equal to mg. We can solve this system of two equations and two unknowns to find theta. We're going to divide one by the other. Normal force cancels out, mass cancels out. Tangent of theta is v squared over rg. And we can solve for what theta is, in this case, about 11 degrees. What if the car goes faster than the design speed? Well, in that case, right, you might say that we need some friction. And this is the case even if it's going slower than the design speed, the friction would help as well, right? The centripetal force is now no longer the normal force in the radial direction. It also has a component of static friction. The normal force itself also ends up changing to a different value. If the car goes slower than design speed, the friction is in the opposite direction. And the new expression for centripetal force is subtracting some static frictional force, right? Because we don't need as much force in the radial direction. And the normal force, again, is going to be different. What about a plane? What makes a plane turn? Well, in that case, the force of lift replaces the normal force. This is from the wings. But the angle information is still the same. We still find that the angle you need is tan theta equals v squared over rg. So that's it. Some examples of those. And you can go back and look at that, other slides, or this video.